Hello, everyone. Good morning, good afternoon, and good evening. Thanks for coming. To the organizers of the conference, especially to the tireless Professor Tawfiq Mansour, I would like to say thank you for having me. I'm honored and humbled to happen to be on the list of speakers and to be monitored by such a distinguished audience. Where should I begin? I ask myself. The king in the Wonderland said, begin at the beginning, but I'm afraid I might end up with the beginning as well. Anyway, let us get started with the idea of a programming language or a formal language, which might sound irrelevant and even bonkers. But please bear with me for a second. As one can imagine, the fundamental issue of a programming language is to regulate every sentence so that there is no ambiguity whatsoever. You cannot simply say one thing and mean another. The machine does not have to read the tone between the lines like in a diplomatic statement. Then the salvation came from the revolutionary concept, namely the idea of a context-free grammar. To make a long story short, a context-free grammar consists of a set of production rules. Each rule plays its own part regardless of the context. Just like you do your duty and you do not really care what other people think about you, contrary to the real-life scenarios. While the grammars we are concerned with are not exactly the same as in practical use due to completely different purposes. So is it far-fetched to relate to context-free grammars? You may ask. I can't answer in one word. Let us consider the derivative property. So does this ring a bell to you? If you stare at it for some time, you may wonder if a derivative operator is context-free in the sense that when D is taking an action on F, it is none of the business of G and vice versa. As an after-event wisdom, it is not insane to claim that the ideology of context-free grammars can be traced back to the concept of differential operators. Even if it were true, it would be a pointless and worthless truth. But there's something to it when it comes to certain situations regarding combinatorial enumeration, and some combinatorial structures are intrinsically context-free. Such context-free properties may look inconspicuous and some may have been taken for granted. But they may have the potential to accomplish formidable missions like secret agents. This is truly the embarkation point of our journey. Instead of projecting decorative theorems and dwelling on rigorous derivations, I have a feeling that it's probably more authentic, rather, to be less formal and to just have a chat about some basic ideas and intuitions that are not touched upon in the technical publications. Let us be a little more serious. Consider the grammar F to F. What is the derivative of F inverse? The answer is as follows. So the derivative property demands the following relation, which gives the answer. On the other hand, in view of the Chen rule, we get the same result. So look at this lovely minus sign here. It tells that the formal derivative D behaves like a sign reversing operator. And then This property reminds us of inverse relations. Let's turn to the classic example of the Umbral calculus. Rota's magical interpretation of the old-fashioned symbolic method by using linear functionals demystifies the illusion of lifting a subscript to a superscript by the following linear functional. And benchmarking example is the following inverse pair. So does the above grammar have anything to do with Umbral calculus? Yes, it does. Let's see how it works. Treat this sequence B naught B1 as a sequence of symbols or variables or indeterminates bearing no meaning, defining the grammar as f to f bi to bm plus 1. It's a shifting operator. Let D denote the formal derivative with respect to this grammar. Suppose we have the relation on the left. By the Leibniz rule, we get the following expression. And you do some very simple, just rewrite it, and you get the inverse relation because the derivative operator acts like just put a minus sign. So you get this, just this derivation is completely rigorous, and it's as simple as the Umbral calculus. So the above reasoning may be related to something elusively remarked by Professor Doron Zellberger in his review article on the Umbral calculus. I must confess that I'm ignorant and likely going to be even more so of the early history on the subject. Nevertheless, we got move on. As the next example, let's consider the grammar x to xy, y goes to xy. This grammar is related to the Eulerian polynomials involving the number of descents of a permutation. It was formally presented by Dumont. In fact, this grammar led us to the notion of a grammatical labeling. Here we remark that the two variables x and y are needed in order to perform the grammatical calculus. First, we encounter two choices of notation. On one hand, a grammar is represented by a set of substitution rules. On the other hand, it can be encoded by a differential operator. So this is a, we call correlation operator rather than an annihilation operator. Dumont argued that the grammar notation has certain advantages. On the other hand, he did not elaborate on the advantage of the operator notation in doing experiments with computer algebra. So the above operator can be perceived as a derivative defined by, you just take x to xy and y to xy, you do the following computation, like xy, you use this derivative property and use this kind of the grammar property, and you do this very formal but rigorous computation. At the end of the page, you get the Eulerian polynomial for n equals 3. Here is a bivariate Eulerian polynomial for an xy, but it is essentially equivalent to the single variable version. Dumont observed that this grammar can be used to generate the Eulerian polynomials in two variables. And he used a recurrence relation to prove this relation. And as will be seen, the above relation has a proof without words. It just takes an illustration. So we're going to discuss a grammatical calculus by making the derivative d as a formal derivative. Here's a generating function. And this is probably familiar to many of you. You have the generating function of the ordinary polynomials it's essentially equivalent to this bivariable version. But for our grammatical calculus, we do need two variables. Okay. But look at this carefully. And what is this? And the inverse equals trivial. And the next step is equally easy. But here is one point that we should discuss. The factor x minus 1 is something special to D. According to the grammar, both x and y are substituted by x, y, but x and y are supposed to be different variables. What is really going on here? The answer is xy is a constant with respect to the operator D. This is a little strange. At first glance, one would not look upon x minus 1 as a constant, as one is used to what is meant to be a constant. However, this individual D has his own judgment, because what matters for D is merely whether the derivative x minus 1 is 0. Once this constant property is established, so we can easily get the following relation, or we can do the following computation. Consequently, we are led to the generating function of x inverse. And we have this obvious relation. So this implies that we instantly arrive at the generating function of the bivariate ordinary polynomials. Are you convinced that this is all the computation we need? Could it be simpler? It might seem a little odd that this innocent-looking constant x minus 1 does play a crucial part beyond expectation. But I can assure that this is all we need, all the computation we need. If you're not convinced, we have more examples to come. As promised, we have a grammatical labeling of permutations. And I don't have to get to the details. So you have a permutation, and you use x and y to label the positions that you can insert n plus 1 into a permutation of n elements. And actually, this labeling scheme is essentially the same as the descent word of a permutation, or the AB index of the symmetric group in non-commutative variables. There are many papers on this, and we listed two of Professor Richard Stanley. And this is a proof without words. You have x and y, and you want to compute the ordinary polynomial, and the grammar surfaces to give you the solution. And actually, we don't have to do any computation. You just look at it, everything is there. And we have to mention that the update is apparently a local, a context-free operation. That means the change of descent only happens locally. It's a local property, so it's in other words, it's context-free. Then we move to the next concept, the peak polynomials. What is a peak? There is a line that is perhaps not entirely unfit. So this is a peak of my career. Well, the peak of my life, really. But what for permutations? Well, first of all, special attention has to be paid to the first position and the last position. Thereby, we are faced with three types of peaks: left peaks, interior peaks, and exterior peaks. By symmetry, right peaks can be treated equally as left peaks. So there have been various and sporadic notations for the 3 or 4 kinds of peaks. We found it hard to set our mind to which to follow. So we felt relieved, at least to ourselves, that we came up with a possible solution, and we hope that they are acceptable to you as well. On this, there are preferred alternatives. Here is our proposal: L for left peaks, M for interior peaks, and W for exterior peaks. Recall that as far as a left peak is concerned, a 0 is patched to the beginning of a permutation, and the other 3 types of peaks are defined in the same fashion. The following illustration reveals why. You just look at it. I think this is a reasonable choice of notation: L, M, and W. There are too many notations in the literature. Incidentally, M is reminiscent of middle and W of wide, in contrast with interior and exterior. The bivariate left peak polynomials are defined by this relation in terms, let's say, generative function, or the number of permutations of n with k left peaks. The grammar for the left peak polynomials was discovered by Ma and via a recurrence relation and independently by us. In terms of a grammatical labeling, Ma further noticed that the grammar can be employed to generate the exterior peak polynomials. Here is the grammar. You take x to xy and y to x square. The former derivative is d, so we'll have this relation. You take this former derivative n times to the variable x, we get the bivariate left peak polynomials. So there's a kind of, if we take the one variable version, David Barton established a system of partial differential equations, and he got a formula, but which requires one more step of integration. An explicit expression of the generating function of the left peak polynomials was given by Professor Gesell. Alternative proofs of these formulas for the left peak polynomials and middle, the interior peak polynomials, have been given by Yan Zhuang. Here is a bivariate form of the Gesell formula. Once you're used to it, it's really neat. Now we would give a one-line justification or grammatical calculus to get to the Gesell formula. Observe that y squared minus x squared is a constant, because we have this, using this grammar, we have this relation. Once we have this constant property, we can compute the formal derivative of x inverse, and if we take parity into consideration, we get the following run. What is this? There's two relations. So if we take the generating function, we get So we see how the hyperbolic functions come on the scene. For the rest, so Bob is your uncle, as we say in UK. That's something I just learned. I hope that I didn't miss anything. Actually, it took us quite a while to reach this point, largely because we did not anticipate such a shortcut. We were nearly there, but we missed the target in the previous pathetic attempts. So a grammatical labeling for lift peaks, to leave no doubt about the rigor of the grammatical apparatus, we are obliged to provide a grammatical labeling. Once this step is finished, before you know it, you may have a proof without words. The procedure is straightforward. So we can display a permutation in the style of a path, more or less the same as the mountain range view of a permutation, as described in the book of Peterson. Then label the steps of the path wherever there is a peak, there are two x's. The remaining steps are labeled by y, just like this. So left peaks, you put two x's. Here we use red color, and the remaining steps are labeled by y. Obvious, and it's very simple, but this is the grammatical labeling, and the judgment is just a proof without words, and we don't have to even think about the notation for the ordinary numbers. And actually, this grammatical labeling is precisely what is needed to put the grammatical calculus on a firm footing. Now we have two more examples to play with this simple grammar. The idea of transformations of grammars can be mobilized to prove combinatorial identities. Here's one stone for two birds. And we just make this change of variables. What happens to the grammars? So it changes one grammar for the ordinary polynomials to the grammar of left peak polynomials. What can we do with this transformation? And this is a simple judgment of the transformation. Okay, first application of the transformation, and we have the bivariate form of the Peterson identity. So as long as we are furnished with the transformation on the two grammars, it is simply a matter of formality to bring out the connection between the ordinary polynomials and the left peak polynomials. And the proof is really just one line. Here we also encounter the constant property of the ordinary of the grammar for the ordinary polynomials. Okay, so let's move on to interior peak polynomials. That means a peak cannot happen at the beginning or at the end. We only allow peaks in the middle. Okay. Here comes the Stanford identity, relating the ordinary polynomials to the interior peak polynomials. And this was derived in the theory of enriched P partitions. Brandon discovered it, utilizing the modified Forta-Strail action. Let's see how we can prove this, we can justify this. And it's really one line, or we don't have to do anything. It's just, we do this change of variables, we get the relation automatically. There's another story using the grammar. We have this nice generating function formula due to anxiety noise, which is concerned with the enumeration of permutations of n with k proper double descents. But in a general setting, a grammatical calculus has been carried out by Fu. A refinement of the grammar for phonetics is given below. It just takes this simple grammar. So it is not clear whether this grammar measures up to the computation of the joint distribution. And the formula of Fu turns out to be a unification of the formula of Gesell and the generating function of anxiety noise. And this is Fu's formula. And if you take special cases, you really get a unification of these two formulas, which is not clear how can you come up with a unification of this two kind of generating functions. I think that's quite a remarkable feature of this generating function. Here comes the story about the gamma positivity. With the aid of a grammar, the gamma positivity of the Euler polynomials becomes transparent. Mama Ye made a change of variables. Just do this change and see what happens to the new grammar or the new operator. You get this grammar. You get a new grammar like U to UV, V to 2U. Easy, trivial. And it's kind of silly to say this. This new grammar is obviously negative, non-negative. Why we say that? We don't define how we didn't define what a grammar is negative or non-negative, but we see that there is nothing negative there. So it must be non-negative. So there's no question about the gamma positivity. Moreover, they transformed grammar, then the new perspective on the combinatorial interpretation of the gamma coefficients. Based on the grammar, we found that the increasing binary tree and increasing plane tree settings seem to be more convenient than the permutation setting to deal with the gamma positivity. So this argument can be pushed forward to deduce the e-positivity of the trivariate generating function associated with three statistics of Stirling permutations introduced by Gesell and Stanley. These polynomials were introduced by Dumont and are called the trivariate second-order Eulerian polynomials. They are generated by the grammar. And the refined recurrence was given by Hageland and Wiesenthal. So in addition to the numbers of ascents and descents, Bola independently introduced the notion of a plateau in a Stirling permutation and showed that all the three statistics obey the same distribution. Here is an interesting story. Ma stumbled on a paper of Dumont in French, and thanks to the machine translation, he realized that the notion of a plateau in a Stirling permutation defined by Bola coincides with the statistic defined by Dumont under the name of a repetition, in French, of course. For permutations, we still have a little more to discuss. For up-down rounds of permutations, it seems to be an everlasting topic in enumerative combinatorics to inspect the number of up-down rounds of a permutation. Roughly speaking, the number of up-down rounds equals the number of turning points. In particular, Alternating permutations are a special class of permutations with a fixed number of up-down rounds. But here is a grammar that can be used to deal with the enumeration for up-down, for the number of up-down rounds. This is a grammar found by Ma. As expected, one can carry out the grammatic calculus to derive the generating function. This has been done recently. In the traditional way, as a first step, one tries to establish a recurrence relation by a clever counting, as Professor Stanley would have put it. Even this is done, we are left with the tasks of setting up and solving an equation. Here we don't intend to compare the grammatical fantasy with the classic strategies. I'm inclined to stick to the belief that sometimes, well, the old ways are the best. Apart from the grammatical calculus, we found that the grammar can be helpful in constructing bijections, and it can serve as a guide to discover something new. It is well known that ordinary numbers can be interpreted in terms of alternating permutations, and even increasing trees whose zth of Peck and Postnikov have given a bijection. We extended this bijection to incorporate the number of left picks. Our construction is somehow rather technical, and we found it more and more difficult to remember. While with the grammar in hand, we were much better off, and we were able to build a natural correspondence which maps several permutation statistics involving up-down rounds and picks to tree statistics involving the parity of the number of children of each vertex. The theorems are eliminated here. The trick can be described as a reflection principle. Hopefully, we have hunted a most wanted correspondence between permutations and increasing trees that can be restricted to alternating permutations and even increasing trees. In summary, if a suitable grammar is at disposal, and if we were lucky, it may happen that this very grammar can solve everything all at once. So we have the last part of the story about enumeration of trees and grammars. So Professor Dominique Dumont was a great advocate of grammars and made a number of remarkable discoveries. What I found the most striking is a grammar for the Ramanujan polynomials in connection with Shor's refinement of the classical formula of Kenny. I never had the pleasure of meeting Professor Dominique Dumont. To show my appreciation, I expressed my wish to invite him for a visit. He kindly accepted the invitation and even made a plan, but sadly, it was a profound regret that he didn't make it. Now, all there is to say is that his mathematics remains to bring me joy and happiness. When speak of Ramanujan, it's hard to connect him to the enumeration of trees. He may not have been aware of what he had done in combinatorial terms. In the monumental edition of Ramanujan's second notebooks, compiled by Busburnt et al., the Ramanujan polynomials have ultimately found a permanent residence accessible to combinatorialists. Jiang Chen should be attributed for observing the connection between the Ramanujan polynomials and Shor's interpretation. This relationship brings the grammatical calculus to the territory of rooted trees and Abel type identities. We shall demonstrate how a grammar can be employed to deal with an Abel type identity arising from the theory of machine learning. Once we have the grammar in place, the identity turns out to be a disguise of the Leibniz formula. This conjectural identity has attracted quite a few combinatorialists to try their hands from different angles. To my surprise, this is not the end of the story. One day I was contacted by my friend, Professor Zhou at Tsinghua University, a geometer, about Ramanujan polynomials and something strange to me, such as the orbifold Euler characteristics of moduli spaces of stable curves. While being astonished, I responded with a question of how he could have the faintest idea of something in our trade. His answer was comforting. He tried his luck with the online encyclopedia, and the search result put us on a common ground. Later on, it came to my mind that this was probably the hint that I should make a donation to the foundation. A question as to the Ramanujan polynomials. Sure, ask a question of give me a combinatorial interpretation of a recurrence relation. Victor Gore and I worked out a rather tedious projection. We knew that it was not the one we were looking for. Then Gore went on to find a simpler construction, yet I still prefer to see something simple, not just simpler. So this is a recurrence relation to define the Ramanujan polynomials. If we use Q as a variable, then we have this polynomial and we have this Q log convexity. Remarkably, Professor Sacco proved that established the total positivity of the Hankel matrix consisting of the Ramanujan polynomials. And this is a short interpretation of the Ramanujan polynomials in terms of the notion of improper edges of rooted trees. And essentially, this is very related to the subtrees has this increasing property. It's kind of the consideration of subtrees that are increasing, but you have this connection, we have this consideration for the edge, on the edge, not on the root vertex. But if you think about it, it's very clear. It's quite natural. And this is something very remarkable. Dumont found this grammar, a to the a cube is goes to a square. And this grammar really captures everything about the Ramanujan polynomials. Okay, this is just some illustration of the labeling, and I don't want to go to the details, but it gives you an impression of how it looks. Oh, this is a final story. And we have abiotype identity. And actually it falls into the framework of the grammatical calculus. This is identity on tree kind of, obviously identity on the enumeration of trees. And this identity has been proved by several people using Umbral calculus, using Cauchy's integral formula, and we have a combinatorial interpretation, and also by the Lagrange inversion formula. If we rewrite it and then use this grammar, we have the following convolution formula. it's just you expand this by you make this expansion and using the Leibniz formula, and you get this trivially. And if we think about the combinatorial interpretation of whatever, we just get this at once. You really don't have to prove it once you have this grammar. So I think it's probably time for myself to ask a question. Usually, at certain point during my lecture, I would ask my students whether they wanted to hear more. I always got a no without thank you. The late Professor S.S. Chen once said something like, the highlight of a meeting comes at the moment of making an announcement that everyone is looking forward to. Now, here it is. Thank you, and thank you all.